Thank you for this second invitation. And so, as Professor Wang said, we started our program at GANIL, and then we have progressively moved to RIKEN. And today I will talk about specifically two-neutron interaction in nuclear decays, and I will select examples from both our last GANIL experiments and then the experiments at RIKEN. So first, before going to the outline, just this is a picture that illustrates quite well the importance of two-neutron interaction and two-neutron pairing. So this is the chart of nuclei, and here you have in the z-axis you have the energy of the first particle threshold, and you can see clearly the value of stability, the proton dripline, and the beginning of the neutron dripline. Here, of course, this part of the neutron dripline has not been reached yet, but you see clearly the odd-even staggering here due to the neutron interaction, and here due to the proton interaction. So, of course, due to the absence of Coulomb repulsion, the landscape on the neutron side is much larger. So this is one of the reasons why we are studying these exotic structures on the neutron-rich side. And here you see a cut on the boron case, and you see clearly, even more clearly, the odd-even behavior due to this two-neutron pairing. Of course, understanding these phenomena are important for to understand why these systems here don't exist, to locate the part of the dripline that we still don't know experimentally, and then in the places where we are able to go beyond the dripline to understand the properties of these resonances, very neutron-rich, that can have also an impact in some parts of neutron stars. And here you have a similar cut for boron here, but for hydrogen and helium. And there are other phenomena that appear in this low charge area, like, for example, the helium anomaly, which is here. You see that typically, like in boron, the dripline goes from the value of stability, goes down to 0 to the dripline, and in helium you have an increase for helium-8. For hydrogen-7, it's still not clear if we have also this increase, but here what you have is, on the right, you have the binding energy per nucleon of n equal 4 isotons from beryllium-8 to hydrogen-5, and you see that the next one would be the tetraneutron, and it could be close to 0. So this is one of the programs we are undertaking to understand the structure of hydrogen-7 and its connection to these tetraneutron systems. But today I will only talk about two-neutron system. So the main issue will be when we study unbound systems, like this scheme here. You have a system above the separation energy of the two neutrons. So we can measure these neutrons and try to understand the structure and correlations of the system. When the system is bound, even if it is weakly bound, we have to break it. So by excitation or other means, we have to take it beyond the separation energies in order to measure the neutrons, and this may have an impact on the information that we are going to obtain. So the outline of the talk, so it will be First, I will give some general concept of the two-neutron interaction. This is the introduction and the context of the problematic, and then I will try to review some. So the two-neutron interaction is something important, but then what is important for us is the connection of this interaction with physical phenomena. And I will try to go through some examples of physical phenomena that are quite diverse, as you can see here. We will see if we have time to go through all of them, or if not, I will just maybe skip the last one. And also, of course, there is the problematics of multineutron emission, but this we covered a bit in the first talk that I gave. So today I will concentrate on the two-neutron case. So for this, I will use some examples that we measure at GANIL of helium-6, lithium-11, beryllium-14. So first, the two-neutron interaction is attractive. So the S-wave scattering length is quite big, almost minus 20 Fermis. So the fact that the value is large and that it is comparable with the size of nuclei makes that in almost all experiments in which we are going to observe pairs of neutrons, we will see an enhancement at low relative energy. So this is due to the fact that the interaction is strongly attractive. Not enough to bind the system, but it's strongly attractive. And so we will see an enhancement at low relative energy, but also any other observable related to it. For example, relative momentum, neutron-neutron invariant mass, neutron-neutron reduced relative energy. So maybe this one will be the one that we will use the most today. This is the relative energy normalized to the total energy available. So it goes from 0 to 1. 0 means that the neutrons have no relative energy. 1 means that they have gone in opposite directions to share all the energy of the system. And already in the 50s, Watson and Migdal, they gave, so with this scattering length, the shape characteristic of a virtual state that starts at 1 and goes up for 0 energy to a very high value given by the scattering length. So this is the shape of the virtual state when you multiply by the phase volume, for example, in a 3-particle decay. This red line times the phase volume will give you this red line here. So what you should see is some peak at relatively low relative energy and just phase space at high relative energy. Then, in general, when we talk about correlations between two particles, and in our case, two identical particles, there are different origins for correlations. For example, the statistical symmetries. If they are fermions, there is an anti-correlation at low energy. If they are bosons, it's a positive correlation. You have a final state interaction. If it is attractive, you have an increase at low energy. If it is repulsive, you have a decrease. And then you can have, for example, a resonance that decays in these two particles. And then you will see a correlation around the mass of the resonance. And you can also have a more complex resonance, multibody, that will impart decay into these two particles. So all these possible effects of correlation, they have different sensitivities. So the first two are sensitive to the source size, and these are the ones that are used in interferometry type of studies. Because of course, these two effects, if the source is very small, then the particles will feel each other much more. If the source is very big, then particles will not feel each other and there will be no effect at all. So you can link the correlation that you see with the size of the source. And these two have nothing to do with the size. They just depend on the structure of the two-body or the n-body resonance. In the neutron-neutron case, the statistical symmetries are negligible compared to the final state interaction. So to this is a strong attraction. So we should see enhancement at low relative energy. Of course, there is no dineutron resonance, so there will be no dineutron that decays into two neutrons, so we don't care about this. And if the two neutrons are in a given complex initial state with initial correlations, then these initial correlations are not restricted to low energies. They could also manifest at high energies. So a signature of these effects could be found if we saw an increase of the neutron-neutron signal at high energies. But as we will see today, in the systematics, in the experimental systematics, we always see signals at low relative energy. And we started our work at GANIL using this reference here that gives an analytical form for this final state interaction. So it assumes that the source has no structure, so we are not dealing with this this part of the scheme here. But assuming that the source has no structure, then this is an analytical form that links a simple source, Gaussian source, with the signal that we could see. So, as I said, at the end of the 1990s, we tried to apply this technique to the Borromean systems. So, two neutron halos. When you break the system, then you have the neutron-neutron interaction that will act on the neutrons. And then, so we concentrate, as I said, on this effect. Only we neglect the initial correlations and we only try to describe the data using the final state interaction, this interaction here. And these were the results that we obtained. So as I said in the Lednicki paper, the advantage is that you have an analytical form. Since the source is Gaussian, then the only parameter is the size of this Gaussian, and then with only one parameter, you can trace the correlation function. So that you see here for helium-6, lithium-11, and beryllium-14. Now, here the parameter we chose was the relative neutron-neutron momentum. And the red lines that you see here describe the data quite well and correspond to this formalism. And below, you can see a plot. So each of these red lines corresponds to an average neutron-neutron distance, and you can see them here. So on top, this is the famous Tanihata picture of the whole, the overall size of the nuclei, and you see here the halo systems, beryllium, so this is lithium-11 and beryllium-14 and helium-6 that are bigger than the others. At the bottom, this is our result on the neutron-neutron distance. So here you have an average size. Now on the bottom, if this assumption is right, you go inside the system and you measure the average distance, and you see that the distance are quite high. So the solid line corresponds to a liquid drop here and here. So you see that the system is bigger than the liquid drop, and the relative neutron-neutron distances are also bigger than the liquid drop, about 6 Fermis. Then there were this paper here from Grigorenko tried to analyze this case, and he reached conclusions that were contradictory to our work in interferometry. For example, this was a toy model in which you have a three-body system, a core and two neutrons that can be in S wave, P wave, or D wave. And you see here this reduced energy, neutron-neutron energy between 0 and 1 for different total energies. And you see that in the S wave case, only in the S wave case, you have this increase of low energy. But if you have a P wave or a D wave, the structures are more complex. And even in the case of the D wave, you can have the maximum close to 1. So this is contradictory with the final state interaction model. And the other test that he made in this paper was take the S wave case and just multiply the wave function, scale the wave function by a factor of 2, almost a factor of 2. So you have here the wave function for the S wave case, and here an artificially expanded wave function. And when we calculated the relative energy, so the solid lines correspond to the compact case, the dashed lines to the expanded case. And he said that there was no sensitivity to the neutron-neutron size. So for him, all that we see in the final state is related to the structure, not to the size of the system. And just to end this first part of for the introduction, when we talk about correlation, we have to understand with respect to what. So what is the baseline? We are measuring something. How can we say it is correlated? So there are different baselines. For example, the work we did at GANIL at the beginning, and also in many other fields when people use interferometry, is event mixing. By event mixing, you have what you should have measured without correlation, and this is your reference. You can also in few body decays, you can have phase space as a reference. So 3-body phase space, for example, or sequential here 2-body phase space. And of course, you can also have a microscopic calculations of the structure. Then in these 3 cases, this is the baseline. And you have to add to this baseline the neutron-neutron final state interaction. In this case, the microscopic calculation has already the neutron-neutron interaction built in. And these are some examples. So in the event mixing case, you have this, for example, one heavy ion collision where they measure the correlation function of neutrons using this event mixing technique. There is our work at GANIL. Here you have, well, on the right, you have the calculation of Grigorenko, where he makes a 3-body calculation with the neutron-neutron interaction included. And in this central case here, this example is the claim of MSU in 2012 of a dineutron decay. So they compared the data to phase space only, to these 2 phase spaces, but they didn't include the neutron-neutron final state interaction. And by not including this, of course, the best description of the data was the dineutron scenario, but this was because they had not included the final state interaction in the phase space. We discussed this in this reference below. So now with this, I finished the introduction and I move to the examples. I listed here to show you that we have covered quite a long way along the neutron drip line. And I will start with the interferometry results that we obtained at GANIL that I have already showed you in the introduction. So helium-6, lithium-11, beryllium-14. So as I said, this was a pioneering experiment. So it was the first time we were going to do this. And we used this simple model final state interaction model by Letnicki. And in this model, there are two strong approximations. The first one is momentum independence. So W here represents the source of the neutrons. X is a relative variable. It can be relative momentum, relative energy. And in this model, the source does not depend on momentum. There are no initial correlations. You have independent particles in the source, and the momentum focusing is only made by final state interaction. So schematically, you have two neutrons with a independent momentum distribution, and the final state interaction will focus their momenta. The attractive interaction will align their momenta. And in this model, when the neutrons are close, the effect is bigger. When the neutrons are far away, the effect is smaller. And so you have, this is a function of the average neutron-neutron distance. On the other hand, if you have a microscopic correlation, so the source depends on the relative distance, but also on the relative, X here was the relative distance, not the relative energy. So this is the source of the neutrons, the geometric source. So here, if the source depends on the relative distance, but also the momentum of the neutrons, then you can have a microscopic initial focusing. For example, like this, you can have the neutrons like this in the wave function, or like this, for example. And in this case, you will have a strong low energy signal or a strong high energy signal. That has nothing to do with the distance between them. It has to do with the microscopic correlation. And so the final state interaction model assumes that this source that can depend on this distance and momentum depends approximately only on the distance. Or in practice, since we measure momenta in our experiments, what we do in our experiments is we integrate the source over the distance in the source. So what we assume, or what this model assumes, is that the integration of the source, of the initial correlations in the source, is negligible. The effect is negligible. So it's like you could neglect them and have only the geometry of the source. And this geometry, you will link it with this relative distance. So the first approximation is momentum independence. The second one is Gaussian source. This Letnicki model, he uses a Gaussian source because this gives an analytical form. It's just for simplicity. And of course, some people said that hadron nuclei are not Gaussian. But what we are measuring is a relative distance. We are not measuring a size, we are measuring a relative distance. And in this reference here, we show that, for example, if you take a one particle distribution, for example, a spherical is the dashed line. We are in logarithmic scale. So this is a spherical distribution. The solid line is a Gaussian, and the dotted line is a Yukawa type. So these three distributions are completely different, but if you fix their size to have the same root mean square radius, then these are the neutron-neutron distances. So you put two neutrons in this volume and you calculate the relative distance, two independent neutrons, and you see that the three shapes are very similar. So even if the starting object has a very particular shape, when you measure relative distances within the object, you are less sensitive to the shape. So in that sense, the Gaussian approximation is not so extreme for these systems. And then this is another view of what we did at GANIL. So this is a sketch of the experiment with the demon detectors for the neutrons. And here you see the result for lithium-11. So this is lithium-11 into lithium-9 and 2 neutrons. This is the momentum, relative momentum between the neutrons. the solid line, the blue line here is obtained by event mixing. And when you add to this event mixing the correlation function of Letnicki with a Gaussian source here, then you obtain the pink line for 6.6 average neutron-neutron distance. So you see that it works quite well. Here you have another take on this with a Dalitz plot. So here you have neutron-neutron relative energy, core neutron relative energy for beryllium-14. And so this is a Dalitz plot that should be flat if there are no correlation, and you see the neutron-neutron signal here. When you project on the neutron-neutron and the core neutron axis, you see specifically in the neutron-neutron one, you see here the phase space. This is the baseline. And then when you multiply the phase space by the correlation function for this relative distance, 5.6 Fermis, you get the pink line. So you see that in relative momentum on relative energy, we have a very, and using event mixing or using phase space, the description of the data was very good using this approximation. Then we chose another example at GANIL, helium-8. In these first three cases, we chose Coulomb breakup because we wanted the breakup to be direct, so the two neutrons emitted at once. But for helium-8, we chose to see if we could be sensitive to the time, not only to the space. And that's why I call this neutron chronometry. So in the helium-8 case, if you use a carbon target, you can break it into helium-6 and 2 neutrons, but you can break it sequentially also. So you can go to helium-6 plus 2 neutrons or to helium-7 plus 1 neutron. And then you have, with the lifetime of helium-7, you will have the same final state, helium-6 plus 2 neutrons, but in the sequential case, the 2 neutrons are not emitted at once. And in Letnicki formalism, it is a space-time formalism. So in the direct case, you only have one parameter, the size of the Gaussian, but in the sequential case, you have also the delay in the emission of the 2 neutrons. So in principle, if it works, you should be sensitive to the size of the source, but also to the delay between the emission of the two particles. And so we published this in 2019, but this is experiments from the beginning of the 2000s. So we took a long time to publish. Here you see helium-8 breakup on carbon. This is the Dalitz plot. So you see the neutron-neutron signal. It is not very strong. You see here in the projection, but in fact, it is because you have only 30% of direct contribution and you have 70% of sequential. The sequential, you can see it here in the helium-6 neutron axis. These two peaks correspond to the helium-7 ground state. And then what we did, we fitted the whole plot with a superposition of these two scenarios. And you see here the 30% of sequential gives almost no neutron-neutron signal, and no, the 70%, sorry. The 70% sequential gives no neutron-neutron signal. Only the 30% direct gives an increase here. And on the other side, the 30% direct gives almost no signal, but the 70% sequential gives this strong two peaks. And then what we did was we made a chi-square comparison between simulations and data, varying the size, but also the delay between the neutrons. And this is the chi-square plot. And you see as a function of the delay between the neutrons and the distance between the neutrons. So you see a minimum in the distance at about 7 Fermis, but you also see a minimum in the delay at about 1400 Fermi over C. And the interesting thing is that if you check, so this is the delay that we measure between the neutrons. If you check what would be the delay associated to the lifetime of helium-7, it is exactly this. So it's in very good agreement with this 1400 from the width of helium-7. So this was a overall check. And finally, we also had data on helium-8 on lead. So here you have Coulomb breakup, so you don't have, or you have a negligible sequential branch. You only have the direct branch. And here you see, when you take the direct components, the dashed lines here, and you plot it on top of the lead data, you see that the agreement is very good. So the picture is quite coherent. It seems like we are able, in this case, to apply this simple formalism and measure average distances and even average delays. And then we moved to heavier systems, carbon-18. This was work done at the ESI by Aldrich Rebel. So we applied this simple formalism to investigate neutron-neutron pairing in carbon-18. The idea, why carbon-18? So carbon-18 is a core plus 4 neutron nucleus. So you can see it here. Carbon-14 plus 4 neutrons. So at that point, we had 2 neutron data. So we had the decay of carbon-18 into carbon-16 plus 2. So what you have is these 4 neutron correlations, but what you are going to detect is a carbon-16 and only 2 of them. And the idea was to study another isotope. So N equal 12, another isotope is oxygen-20. The idea was to look for correlations in carbon-18 and have a reference without these correlations, and we chose oxygen-20. So here you have nitrogen-19, you remove 1 proton and you get carbon-18. And in this case, you have oxygen-21, you remove 1 neutron and you have oxygen-20 that decays into oxygen-18 plus 2 neutrons. So you see here that the separation energies, we are not anymore with halo nuclei. With these nuclei are quite bound. Here you have the binding energy of the 2 neutrons is 5 MeV, here almost 12 MeV. And then what we measure is the spectrum above this 2 neutron separation threshold. You see there are no narrow peaks, it's just a very broad structure. And here you have the simulations on top of what you should see. So we have already seen a Dalis plot for barium-14. Here you have what you should see. This is neutron-neutron and fragment-neutron. This is phase space, which is flat. This is the neutron-neutron signal. So at low, close to 0 neutron-neutron relative energy, you have an increase. This is the fragment neutron resonances. So for a given value of the fragment neutron energy, you have a peak. And then since you have 2 neutrons, the other neutron, there is a mirror effect. So you have the resonance with one of the neutrons, and then the other neutron has, by energy conservation, has another structure. And here you see the combination of both. So you can have, as we saw for helium-8 at GANIL, you can have sequential and direct. If you have direct, you will have this. If you have sequential, you will have this. And if you have both, you will have this signal at low neutron-neutron energy and some kind of croissant here. These are simulations. These are data. So for a given gate in energy, this one here for carbon-18, you have this Dalis plot, and you see that it looks a lot like the final state interaction model. Here you have another gate in energy for oxygen, and you see another case in which it resembles a lot. So you have the partly direct, partly sequential. So the model works well in the description of the data. And of course, our aim is in the future to measure carbon-14 and 4 neutrons. But for this work, we only could measure 2 neutrons. And then here you see the whole spectrum. What we did was, there are no narrow structures, but we make some gates in the energy from the threshold up. So you start to gate, and you have a look to the correlations. And here you have, on the left, you have carbon 18. On the right, you have oxygen 20. So on each of the two panels, you have on the left the data for increasing excitation energy. So we start here close to threshold and we go up in energy. These are the Monte Carlo simulations. And here the same thing for oxygen. You start at threshold, you increase energy, and the Monte Carlo simulation. So you see that the fits, these are fits, are very, very good. And you see that in oxygen, the correlations are weaker, as we expected. We expect them to be weaker than in carbon 18. And very quickly, you have this sequential pattern that you see a bit better because there are no such fluctuations in the simulation. In carbon, the correlation is much stronger, and the sequentiality only appears very, very high in energy and very weak. So this means with this simple model, we were able to describe qualitatively the data. But what about quantitatively? So what do these parameters mean, if they mean anything? So for the source size, we obtain in all cases an average distance of about 4 Fermis. So if you remember, for halo systems it was 6, 7. Here it was 4, which was in agreement with a liquid drop of mass about 20. So it was coherent with what we expected. And then the delay that we observed make the difference between the direct and the sequential emission. So again, we understand that the model is simple, but for the GANIL data that we had and for this GSI data, it worked in the description of our spectrum. Then I moved to more sophisticated cases, more recent ones. So the first case, we will have not a broad distribution of energy, but specific to neutron states. The first example, beryllium-16. I will go very quickly because this was one example we saw in detail in my first seminar. So I only wanted to make one point here. Since today we are talking about the neutron-neutron interaction, this is the neutron-neutron interaction, a typical one, as a function of the neutron-neutron distance. So you see the range, it's about 2 Fermis. About the neutron-neutron distributions that we are extracting from, or we extracted at GANIL, when you have big neutron-neutron size, these are Gaussian distributions, you see that most of the distribution lies outside the interaction. So in those cases, you can just, you don't care about the shape of the interaction. You can only use the scattering length. And this is what is done in the Rednicki model. So one parameter gives you who characterize the final state. But if you have a compact configuration, like we have in some nuclei, then scattering length is not enough. You need the full potential, neutron-neutron potential, but you also need the core neutron potential and even the 3-body force. So you should better use a microscopic model that has all these interactions and not just only one number, the scattering length. And this is what we did for beryllium-16. So we tried to model beryllium-16 in a 3-body model, and then the challenge was to compare the wave function of these states in momentum space with the data. So here we have, from another experiment at RIKEN, heavy beryllium resonances. So this is the Dallas plot for a beryllium-14 resonance. You see this flat, there is no neutron-neutron signal, and I will come back to this later. And the two resonances that we were looking for in beryllium-16, the ground state and the first excited state, you see clearly the neutron-neutron signal. Here you have the projection on the neutron-neutron axis of both the ground state and the first excited state. So the ground state has an important signal. In the excited state, it's even more important. And these are the calculations from Casal for this 3-body system. So this is the wave function. Here you have the neutron-neutron distance and the distance of the neutron pair to the core. So this log here corresponds to a compact dineutron configuration. In the 2+, you see a different pattern. So this lobe disappears and you have a very diffuse configuration. But this is paradoxical because in our first works, we said that compact means strong signaling energy and diffuse means weak signaling energy. So here you see the importance of addressing the microscopic structure of the system. And so what Casal did, in a similar way of Professor Wang also has done for other systems, is to use the momentum, the asymptotic momentum of these wave functions and project them into the relative energy. And you see here, these are results that have been submitted a few weeks ago. We hope they will be published soon. And you see that this model is able to explain the increasing correlation even if there is no compact configuration here. Now, two-neutron state and Efimov trimers. So this is another very interesting case in physics case. And the candidate here was boron-19. So boron-19, we moved from beryllium-16 to boron-19. And maybe people that were not at my first seminar. So I added this slide just to tell you where do we do these things and how. So for boron-19, we do it at RIKEN, and then what we start with a calcium-48 beam, primary beam. Then we are going to break it in a beryllium target. And so you see, in this example, we want to make a secondary beam of carbon-20. So these are all the protons and neutrons that you need to remove in this collision here. And then carbon-20 will reach our experimental room. If we are able to remove one proton, then we have boron-19. And then if it decays into boron-17 and 2 neutrons, we can reconstruct the system. And this is work from Julien Gibelin. What is interesting about boron-19? You already know that the neutron-neutron scattering length is very big, about -20 Fermis. In this particular case, this scattering length is even bigger. So the boron-17 neutron scattering length, there is only one experiment from MSU, and you see here the virtual state going to 0, the boron-17 neutron virtual state. And they could not measure the scattering length. They only gave an upper limit of -50 Fermis. So you have here a 3-body system governed by very strong scattering lengths. And so here you see, when you reconstruct the 3 bodies, here the free body energy. These are excited states of boron 19. So this is the first one, is very clear, and then you have a series of states. So this is work ongoing. So we will publish this soon, we hope also. But this first peak, this first excited state is very clear. So it's very easy to gauge on it and have a look to the Dulles plot. You see, it has nothing to do with the ones that we have seen previously because of this boron 18 virtual state. So this is the boron 17 neutron axis, and you see at very low energy the virtual state. This is the mirror effect for the other neutron. But if you forget for a moment these two peaks, you can see that the neutron-neutron signal is also there, an increase towards zero. So here you see the effect of the neutron-neutron scattering length. Please ask ourselves the possibility of have Efimov trimers. So the Efimov effect, this is a very good review paper, is a scale invariant three-body attraction. So if you have three particles, you need them to be almost bound. So you need very strong S-wave attraction for between the particles, and this is the case here. We have S-wave, very strong attraction, and you have from these two body forces, you have an induced long-range interaction, and the most spectacular characteristic of this Efimov effect is that there are a series of states with a discrete scale invariance. So you can have, of course, you have Borromean binding. So from unbound systems, you get a three-body bound system, but you can have excited states that have just scale invariance. So the structure is the same, but they are bigger. And of course, this has been found in atomic physics. In atomic physics, you can change the interaction with magnetic fields between the particle pairs. In nuclear physics, we cannot. So we have to be lucky enough to find a system that has already these interactions finely tuned by nature, not by us. So it's very difficult to find maybe an Efimov effect in nuclei, but we have Efimov physics. So Efimov physics means that even if you are not at the point of this effect, you can see very interesting phenomena like universality. In the case where the scattering length is much bigger than the effective range. So when you have a scattering length much bigger than the range of the interaction, then the properties of the system become universal. You don't depend on the details within this range. And then, as I said, here we have a three-body system, about -20 Fermis for the neutrons, about -100 for boron 18. And the three-body system is very weakly bound, only 140 keV. So Hiyama-san, Carbonell, and Lazauskas made a calculation of this system using these two ingredients. And this, so you can find the details in this publication. And here, this is a very beautiful picture. So since, as I said, this scattering length is not well known, they let vary the scattering length of boron 18 from 0 to -1000 Fermis. And they did this for two neutron-neutron interactions. And you see that in both cases, you have a weakly bound boron 19. So this was a very good result. Boron 19 is bound. And the first excited states are unbound, which also agrees with what we have seen here. But of course, you could argue that first, the scattering length is not very well known, but the binding energy is not very well known. So at this scale of the picture, these are the error bars of the experimental binding energy of boron-19. So it's good that they found a bound state compatible with experiment, but it's true that it's relatively easy to be in agreement with experiment when the error bars are so big. And now one interesting thing here about this universality is the dotted line corresponds to the result when you take the scattering length of boron-18 to infinity. So you go to minus 1000. If you push it to infinity, you get this asymptotic value so you cannot bind the system more. And this is called the unitary limit. So before the unitary limit, you say that the system depends only on the scattering length. You don't depend on the details of the potential, but at unitary limit, you don't even depend on the scattering length. You take it to infinity and you have the properties of the system that are universal. And the dashed line here corresponds to total unitarity limit. So if we take, in the blue case, the boron-18 scattering length to infinity, and we also push the neutron-neutron scattering length to infinity, and then you get this result, which is also consistent with the experiment. So this confirms that boron-19 can be a very interesting system for unitary limit studies in nuclei. Another conclusion of this paper is that it is unlikely that we have other trimers, so Efimov trimers, and this is because light heavy is not very well suited for this Efimov effect. It would be easier if the three particles had equal mass or if two of them were heavy. So what they conclude is that the scattering length of boron-18 should be of several thousands of Fermis in order to have a possibility of this. And okay, so you see that the neutron-neutron interaction, even when you take it to infinity, it can lead to interesting effects in three-body systems. And then, so now we have only two subjects left, but I think we have the time because I will go very briefly over them. So this one, two neutron states. So I call here transparency, and I put it like this because I'm not sure about. I heard this in a conference. Someone called this effect transparency, but I'm not sure what he meant. So, and an example is fluorine-28 at RIKEN. From Aldrich's work. So I showed you Dulles plots with strong neutron-neutron signals. Then this one where you have also strong fragment neutron signal. And here at RIKEN, in this reaction, so we remove one proton from neon 29 to populate fluorine 28. And in this case, so fluorine 28 can decay into fluorine 27 plus 1 neutron or fluorine 26 plus 2 neutrons. This is the spectrum for fluorine 26 plus 2 neutrons. And you see here a very narrow peak, a broader one, and another one here. And this is the level scheme. So this is fluorine 28. These are 1 neutron unbound systems. These are 2 neutron unbound systems. These three here are the three that we see in the picture. And then the question is, do we go through states in fluorine 27, or do we decay directly to this fluorine 26 plus 2 neutron? And for this, we gate. So unlike the work from GSI, here we have clear peaks. So we can gate on them and we can see the Dulles plot. And you see a very a strong difference. So for this state here, you clearly, so you have a slight increase in the neutron-neutron interaction, but mostly you have these structures in fragment neutron that show that the decay is sequential. And you see here, this, you are going through this state in fluorine-27. So one neutron and the second neutron. And you have this here, one neutron and the second neutron. But for this state, it is completely flat. Of course, statistics are weaker, but you see a very flat Dulles plot. And this is the decay in green here. So the two neutrons leave at the same time, but you see no neutron-neutron enhancement at low energy. And this can be due to the fact that the energy of the total energy available is very weak, is very low, it's 250 keV. And this is what someone called transparency, saying that the energy scale is too small for the neutron-neutron interaction to manifest. And just as a reminder, so I showed you this plot when we talked about beryllium-16. So this is beryllium-14 excited state that is also at about 250 keV. And you see that Dulles plot is also very flat. Then boron-19, we saw that the state was quite low in energy, the first one, and the plot is not flat at all, but you see that the energy was already 680 keV. So maybe it would be interesting to find other cases between 250 and 700 to see if this phenomenon of flat correlations is something unique at very low energy, or is something that progressively appears when we go down in energy. Yeah, so oxygen-26 is also a case. This was a prediction. I think Professor Wang was one of those that predicted that in oxygen-26 that it's only 18 keV. So in oxygen-26 it should be also completely flat, but this has not been measured yet. And just the final example. So the other day we talked also about multineutrons, and I will not talk today, but boron-21 is just a transition. So I thought it would be good to finish with it, because it's at the same time two neutron state, but it could be also many neutron state. Boron-21 is here. So this is work from Sylvain Leblanc that we published in 2018. So you can, there are some interesting things in the mass of these systems, but maybe if some of you is interested, you can ask. But I will concentrate on the emission part of the results. So these were our results. So this is the bound state of boron-19. These are, we found 3 states in boron-20, so boron-19 plus 1 neutron, and we found only 1 state in boron-21 that decays 2.5 MeV to boron-19 plus 2 neutrons. So it was a candidate for what people call dineutron emission, because even if you have a sequential path available, it seems that the decay is always direct. But of course, boron-19 is very weakly bound. So if you have a look to the thresholds, the boron-17 threshold is here. The boron-15, because boron-17 is also weakly bound, boron-15 is here. So this state could decay also by the emission of 4 neutrons to boron-17, or by the emission of 6 neutrons to boron-15. So it could be the first candidate for 2, 4, and 6 neutron emission. So of course, with our the data that we already have, we only have statistics for the 2-neutron channel, but in the future we may try to populate this state and measure 4 and 6 neutrons in coincidence with 15 and 17. So this could be a link between the 2-neutron interaction.
Sorry, my internet is broken. So, are you finished? Okay, so somehow I cannot hear you, but yeah, it's question time. So if anyone has questions or comments, please raise your hand or unmute yourself. Yeah, maybe let me first ask some questions. So, and yeah, it's quite interesting to see in this beryllium 14 2+ state and the fluorine 28, all those correlations kind of flat. And I think in some case in the beryllium 14 the 2+ state is in my understanding is kind of different from this oxygen 26 because it also has the angular momentum. So in somehow in theoretical calculations, usually we think that those angular correlation will go against those flat distributions. So do you have some comments on this? Sorry, I cannot hear you somehow. So is it my problem or is other people can hear you?
And now, can you hear me now?
Yes.
But it has been like this the whole seminar, or?
No, it's just like the first, the last part before the summary.
Okay.
Just one slide.
Okay. Yeah. So, yeah, about your question yeah, I see there is a message. I see one question in the discussion in the chat.
Yes. So yeah, maybe we can go this first. So the first thing is it's possible to emit several neutrons at the excited states for not so neutron-rich nuclei.
Yeah. So this was our motivation here in this work, because at the time we were doing experiments at RIKEN to measure the emission of several neutrons in unbound systems, like hydrogen-7 and others. Then this was work also in collaboration with Olivier Sorlin from GANIL. So he had access to all this data from GSI campaigns that were not at the drip line. So carbon-18, oxygen-20, and other systems that are not so neutron-rich. But he said, okay, but if we excite them, we can measure the neutrons. So the problem is, in this case, for example, or take oxygen-20. So oxygen-20, it is very well bound, but you can always, in a violent collision, you can always excite it and make it emit neutrons. And here you see this channel, so oxygen-18 plus 2. But for this, you need to excite oxygen-20 to 11.6 MeV. So what you see here is the 2-neutron emission from oxygen-20, but starting at almost 12 MeV excitation energy. So you are going to measure properties of oxygen-20 continuum or resonant states, but that are very far away from the ground state. So, of course, the system can emit the neutrons and you can measure them, but then the problem is more in the interpretation. So what are you measuring? Are you measuring some strong correlation in oxygen-20? Or are you measuring some particular properties of the continuum, the high energy continuum of oxygen-20? And here, for example, you see the next threshold. The 4-neutron threshold in oxygen-20 it's here. So you see 12 plus 12, 24 MeV. So if you excite oxygen-20 more than 24 MeV, you can see 4-neutron emission. So it would be oxygen-16 plus 4 neutrons. But you need to excite it a lot, and then what you measure is not very clear. What is the physical significance of this? And for carbon-18, the thresholds are lower because it's closer to the drip line. But again, you need 5 MeV excitation to reach here and to see 2 neutrons. And then you need 5 more, so about 10 MeVs to observe 4 neutrons. So if you go to the drip line, experimentally, there is the problem of beam intensity. When you go to the drip line, the beam intensities are lower. So the statistics will be lower, but you are probing the emission of ground state resonances, for example. If you go closer to the stability, like carbon-18 or others, you have very high intensities, but then you need to excite the system a lot. So you go up in energy, and then you will see the neutrons, but then the link with the properties of the ground state are more complicated to make, because you need already you may be probing different wave functions, but also you need to be sure of your reaction model, because you need to go from ground state to a state at 20 MeV. So the reaction that took you to this state is also important. So all systems have advantages and inconveniences. There is no magical system.
Yeah. So yeah, what about the other questions? So do you have any comments on this? So
about your question here,
yes.
Because what I saw for oxygen-26 was that it was very close to. So when you do the projection on neutron-neutron, it's very close to phase space.
Mm-hmm.
So here is the same thing. When we project here, we have something very close to phase space. Here is the same, very close to phase space. So so even if the structure is not the same for oxygen-26, variant 14, what we found so oxygen-26 has not been measured, but I guess that if the experiment is done with a higher resolution for the neutrons and if they are able to do the Adalis plot for only 18 keV, I guess I'm afraid that they will also find something flat. So I don't know. So it could be that at such low energies, it makes no sense to make a very strong effort to measure because the distribution would be flat. But we would like to, because as I saw here, we have a lot of data. So when we saw this, and then we saw this, then we said that we could just scan all the data that we have and see if we have other states around 250 keV or slightly higher, and see at what energy the structure of the state begins to show up.
And following this question, it's also interesting to see that those fluorine-28 decay directly to this fluorine-26 rather than going to his neighboring nuclei, even though the energy is allowed. So is this also the kind of alignment effect? I mean, just because this state is close to the two neutron separation threshold. So does this mean that the structure is also aligned to this fluorine-26 rather than this fluorine-27?
Yes, and in this particular case, so I said this is from Aldrich's PhD because this part we have not published, but in the paper that we published for 1 neutron channel, we also see the decay of this state here to fluorine-27 plus 1 neutron. So this could be also interesting because some of these states, I think this one and this one have two branching. So one, they can emit 1 neutron, but they can also emit 2 neutrons. This one sequentially, this one direct. So I think that with this data, we could learn about the structure of these two particular states because we have a lot of constraints. So we know the percentage of 1 neutron decay, the percentage of 2 neutron decay, and when there is 2 neutron decay, we know the percentage of direct and of sequential. So I think this is a very complete experimental picture of the states. So it could be interesting to take a closer look to the structure of these states.
Yeah. So what? Which one is dominant? So 1 proton decay or 2 proton decay for this?
But I should check. I don't remember, but I know there is a significant branch because we could use these two states to reevaluate the mass of fluorine-27. So and this is in Aldrich's paper. So if you don't have the reference, I can send it to you. But so it was interesting because this energy difference was exactly the same in the 1 neutron channel and the 2 neutron channel, but there was a slight shift due to the wrong evaluation of this mass. So I cannot tell you the value, but I know it is a significant part of the decay goes to 1 neutron.
Thanks. That's very interesting. So, is there any other questions in the audience? Okay, maybe let me ask another one. So, so in the boron-19, so it's a good candidates for Efimov studies. So, as you mentioned that the scattering length is a key feature for the Efimov physics. Another one I think is also because of the scale invariance. There will be a lot of states for that. So I saw your experiment. You measured a lot of zero plus state above the threshold. Is this a sign of the Efimov state or not?
What do you mean? I the last part of the question I didn't understand.
Oh, so yeah, because the scale invariance. So if we enlarge the scales, there will be another eigenstate of the system. So in principle, for Efimov states, it should have infinite number of states close to the threshold, right?
Yes.
Yeah. So, the first thing is, do you measure this boron-19? Do you get those states for the boron-19 to the bound states? And the other thing I saw in your experiment, you also measured those states above the threshold, and I saw a lot of zero plus states. Is this also a sign of the Efimov state? Yeah, in this figure, right?
Yeah. So this is because we are working on the publication of this, and for this, so we have the energy of these states here, and we have worked with Nicolas Michel, who did the gamma shell model calculation of these states. So this is just to explain the number of states and the spin and parity, but this has nothing to do. This is not a three-body calculation. So this is but on the other hand, we have this calculation from Hiyama-san. So our aim was to see if the unbound states that because this three-body model explains the bound state, but also has some unbound states. And we wanted to try, so we tried to explain this with the gamma shell model, but we would like also to explain it with the three-body model of Hiyama-san. The problem is that the three-body model of Hiyama-san has a lot of free parameters. So trying to do a detailed study of unbounded states, they depend a lot on the exact value of the scattering length here. And also we don't know which is the binding energy. So I didn't talk about this today, but one of our PhD students is working now on the determination of the scattering length. So we have data from Samurai, and with very high statistics compared to this. So we hope that we will be able to give a value for the scattering length. And I think at that point, maybe Hiyama-san will retake her three-body model and try to see if these unbounded states predicted by the model have this Efimov character or not. But for that, she is waiting for us. So she's waiting to see if we are able to locate the scattering length here with more precision and try to reduce the error bars on the binding energy of boron-19. And then she will revisit her three-body calculation and see if these unbounded states can be linked to the unbounded states that we see here.
Yeah, that will be very interesting.
Hey, hello, Simi. Can I ask a question?
Yeah, Sai-Hong, please.
Hi, Sai-Hong.
Oh, hello, Miguel. So sorry, I didn't find the raise my hand, so I wait a little bit. So anyway, so yeah, so thank you, Miguel. This is, I think, really my first time I hear you talking about interferometry. I know this maybe for 20 years, I think.
Very old work.
So I just want to confirm one thing from your talk today. So it seems your point is we cannot use interferometry to study the initial two-neutron correlation for well-defined resonant state, right?
it's not very clear, because when you say interferometry, it depends. So what we did here at GANIL, here, too fast, here. So the correlation function, what we did just event mixing. So you know this technique very well. Event mixing and just the ratio, and see if at low momentum or energy you have some increase. So this you can always do. The problem is, so you can do it here, relative momentum. You can do it. So here, this is the same correlation function that I showed for lithium-11, but here you have the numerator, so the what we measure, and the denominator, the event mixing, and then the ratio is the correlation function that I show in the other plot. And you can do it here also. So this is the relative energy, the Dallas plot for beryllium-14 phase space, and then you measure this. You can do the ratio. So if by interferometry you mean constructing the correlation function, so trying to determine some uncorrelated reference that you compare to your measurement, because the points here are just a measurement. So if you compare these points to phase space, this is a correlation function. So if you call interferometry the construction of the correlation function, you can do it. Now, if you call interferometry the fit of this signal with just a source size, this is what we did at GANIL. So we found these signals, and we said, okay, if we assume that there are no internal correlations, or that they are negligible compared to the final state interaction, can we describe the data? So this was our philosophy. Can we describe the data with such a simple model that has only one parameter? And the interesting or funny thing was that we could describe the data. Then we have done beryllium-16 at RIKEN, and with the model from Casal, we have realized that you can construct the signal, but this number here for me is not very clear. So this is very effective. So we cannot really say that the wave function of lithium-11 has this neutron-neutron distance. This is the result of this effective description. But in the case of beryllium-16, we have seen this. So you have a microscopic wave function that is very compact, and you have a signal, but then you can have a microscopic function that is very diffuse, and you have even a stronger signal. So in Belen PhD, she made the exercise to try to fit this using the final state interaction model. And she found some neutron-neutron distances, but that are in contradiction with this wave function. So you can use the model, and since it seems that we have always low energy signals, the model works, and the model gives you a number. But then, is this number physical or not? This is because in Belen's PhD you can see that you have a number here, and you have a smaller number here, because the signal is. But this number has nothing to do when Casal calculates his average distance between neutrons in the wave function. It doesn't agree with the simple model. And the other. So for example, here it worked. So that's why when Aldrich applied this to the continuum of carbon-18 and oxygen-20, he had an average distance of about 4 Fermis. That seems logical for nuclei of this size. So it seems, so qualitatively it works. If you want to describe low energy signals, this model works. Quantitatively, sometimes it works. but sometimes it doesn't. So that's why if you are going to apply it to a known system, your first result will not be very reliable because you don't know if it is good or not. If you apply it to a known system where you know already the value, then you can check if the model works. This is this is my view of this.
Okay, so still, I think this kind of simple method is still very useful, at least to understand the correlation. Yeah.
Yes. Yes.
Okay. Thank you. By the way, short message. I think we will meet next week. I will write to you, email to you later soon. Yeah.
Okay.
Okay, is there any other questions? So if not, let's thank Professor Marcus again. Thank you very much for your nice talk.
Thank you all.
Yeah, so the seminar is over now. See you next time. See you.
See you.